Welcome to this webinar. Actually, congratulations to the Beju Senadipatan Foundation and Beju in particular, who started this foundation, and it is covering almost every part of the world over the last decade or so. Congratulations to the entire team for the untiring effort that is being doing to make sure that the academic activities or the academic this thing is shared with multiple surgeons across the globe. Kudos to him and his team for doing this venture consecutively for the last so many years. And so many of international faculty and national faculty from India have appeared on this screen, and we are all very happy to be part and parcel of this webinar. Sam, thank you so much for being with us. Actually, you're one of the pioneers. Thank you so much for being with us, and we'd like to hear from you about your experience in digital surgery and how it's going to be shape the surgery in future.
Thank you so much for having me as your guest today on this webinar, Dr. Rao. I'm a huge fan of yours as being the pioneer of notes. This is something when I was training in residency, when I heard about what you're doing, really just galvanized me to start to appreciate what is possible in the future of surgery. And digital surgery is one of those things, and the topic that I'm currently very interested in that we're talking about today, obviously. This is let's see if we can get our slides to go forward. And so what is the definition of digital surgery anyway? I like this definition from literally and exactly a year ago today, from the white paper published in Surgical Endoscopy that defines digital surgery as placing a computer interface between the surgeon and the patient. Now, there's lots of complexities, and it's a dizzying amount of terms when we start talking about computers and AI. I'm going to take you along a pathway on the right. We're not going to learn everything about computers. The purpose is not to become a computer scientist in one talk, but we want to understand some of the key and salient ideas that as surgeons we need to be aware of. So if you follow on the right, machine learning and deep learning, and especially convolutional neural networks and how they fit into modern computer vision, that is what we're going to be talking about. And please excuse the first half of this talk. It's going to review a lot of history about computer vision. And you're going to be wondering, well, how does this even relate to surgery? But I promise you, in the last half of the talk, it's going to all tie in. So please be patient. So that's what we're talking about, computer vision and vision in surgery, which is a huge element of that computer interface between surgeon and computer. So what about our vision? Did you know that about 500 million years ago, evolutionists have looked at this and have felt that there has been an explosion in species that occurred 500 million years ago? Massive. There was really no progress up until that time, and they attribute this to the acquisition of vision. This is what blossomed all of evolution, according to one author describing it as evolution that occurred in the blink of an eye. Well, what about computer vision? Historically, it certainly didn't start 1 billion years ago, right? This started in the 1950s, and the father of AI, including applications to computer vision, Alan Turing, said, hey, wait a second. How did you start out? All of the adults here on this video, did you all start out brilliant geniuses who could operate? Absolutely not. You started out as a kid, and then you got trained, and then you started to learn, and you learned one thing at a time. And Alan Turing believed we had to do the same with computers. And he, quote, said, instead of trying to produce a program to stimulate the adult mind, what we need is to produce a program that simulates a child's mind, and then we can teach it, and then it can be like an adult. So for computer vision, how did we learn things when we were kids? Your mommy said, look up at the sky, that's a bird. And you said, oh, okay, that's a bird. And then you could recognize all birds. And then you could differentiate them from a plane. Computers learn like a child in the same way, but unlike the human brain, which is an exceptionally powerful at visual interpretation, computers need lots of examples, not just one or two, but lots of examples. And we're going to come back to that as we learn a little bit about the history of computer vision and its development. So historically, it started in the 1970s, right? Now, at this time, we had very slow computer chips. We didn't have what we have today. But the idea that computer scientists for vision looked at was deconstructing objects into their primal, geographic primal parts and looking at oriented edges. What does that mean? It means we break objects down into their basic geometric shapes. So this image of a basic image of a vehicle, a car, let's say, is made up of two rectangles and two circles. And this was one idea of how a computer could deconstruct an image and make it have sense. The other idea that came about in computers and how to teach them to see an object is the same way that we will do image segmentation, the same way you take a jigsaw puzzle and it may be an image of the sun and the sky and the ground, and you'll take all the blue images and put those jigsaw puzzles together because you know those blue jigsaws go together. This is the same idea on an image level that we use in computing, and computer segmentation uses this basic principle just like we do when we solve a jigsaw puzzle. But a huge step forward, and I'm moving away from the 70s to the early 2000s, when computers were able to now recognize an image of a face. You remember in the early 2000s, you got a digital camera and you would half push down the button and it would put squares on everyone's face. This was one of the most important developments, by the way. And up on the upper right, I show you how much these papers have been cited. You know, in our literature, 1,000 citations is a lot. You can see and look at that to get an idea of just how important these studies were. So this was the first step, is I just need to be able to recognize a face, not your face. I just need to know it's a face. And so a lot of the things in AI, let me just move this out of my viewpoint. Hang on a second. Oops. Okay. 1 second as I get that out of my field of view so I can talk to you better. One thing that, that we can do in computers is deconstruct a face into its primitive, or like we described in the 1970s, they called it primitive parts, but what we now call features. So a face is made up of eyes and eyebrows and noses and mouths. You know this, right? But computers, for them to recognize a face in different orientations, it's not easy for them like it is for you. We can all know this is faces of women, but we cannot know, or a computer cannot so easily know that. As I alluded to, computers can learn, but they require multiple data sets and examples. So here's where the key, most important progress in computer vision that we're going to see later is applied to surgery, okay, happened. This was it. It was between 2010 and 2012 when computer scientists, not us, not surgeons, not medicine, said, let's do an experiment. Let's get a computer program to find all the images on Google Images, for example, 10,000 images, and let's see how quickly they can be trained to call. For example, if I show it a picture of a truck, it says that's a truck. What we describe when we say that is this, I'm going to show you a cup. Is this a cup? Yes, it's a cup. That's called an image classifier. Okay, so they had these huge data sets that in 2010 exponentially grew over 2 years. From 10,000 images they were fed, but the accuracy was poor. It was only 40%. Then they got from just a year later to 14 million images, and the accuracy did improve, but it wasn't that great, 68%. The breakthrough happened in 2012. At this point, the accuracy jumped up to the 80% range using millions of images that were fed into a system to train it to be able to be accurate at contributing. And that breakthrough in 2012 was deep learning and or often referred to as convolutional neural networks. This is such an important part of the computer interface. We need to understand it as surgeons. We need to know what this huge breakthrough was so that we have some understanding. Again, we're not going to learn to become computer scientists, but we need a background, okay, to be able to interpret what's happening in 2025 now. So this was that paper, by the way, again, cited 119,000 times and published in 2012 that described for the first time convolutional neural networks. And this requires being fed a significant amount of data. And what are we trying to really do? We're trying to have a computer understand how to recognize something not always in its standard form. For example, I don't want it to just recognize, if we're going to use eyes as the feature, eyes when they're open. I need it to also recognize eyes when they're closed, and letters not when they're straight up and down, but when they're curved. So we're going to understand now how this happens. We're going to take a letter X that's 36 pixels, and this is divided into spaces that are either all white or all black. -1 for all white, and for solid black, we'll call it 1. Okay? Because guess what? Computers don't actually see anything. They convert everything into a numerical value. That's something important to understand. And each of this X is also made up of a down slant, 2 down slants, and 2 up slants. You see that? We're taking it very basics, 36 pixel image. And the down slant, then we can refer to as a feature. This is a down slant. It's one little piece that fits in 2 places. It's a feature. So I can teach my computer that feature, just like I can teach it to recognize an eyebrow on the face that I showed you, or the eye of a face. But we're keeping it really simple here, just dumbing it down to pixels, a few pixels. A convolutional network is very simply stated as this. We take that feature that the computer learned and then go all the way around to see where that feature best fits in the given image. And it goes round and round and round in a convolution. And that's what that's why it gets its name, convolutional neural networks. Does it fit best here, or does it fit best here, or does it fit best there? It fits best in the upper left and the lower right. You see, that's all it is. Yeah, there's a little more to it, but this is the dumbed down surgeon need to know level. Now, dumbing it down a little bit further, again, if a computer, we show it one image, it knows one image, it knows this one feature, and we show it the exact same thing, well, it can calculate mathematically the similarity, and these are identical, so no big deal. But what if, and remember, we're assigning a number to each of the pixels, just working this out mathematically. If we had 3 pixels that it knows, and it knows that this is a feature and it's only 3 pixels, and we show it something that's similar, it's not exactly the same. It's 2 pixels, but the other one's not there. So now it has to say, is this the same thing? Is it similar enough that I can say, yeah, that's the same thing? Mathematically, we simply multiply, take the product of each one, as you see there, and then divide by the number of pixels. And we can do this for massive arrays. When we look at millions of pixels here, and we want to see it similar to these group of million pixels, well, we simply just have a mathematical model for that. We don't have to sit here and do all the arithmetic. A computer does that. This is what it looks like. It's called multiplying arrays. It really is no different than what I just showed you here. It's only on a bigger scale. To tell and determine what is the similarity between what I know, my feature, and what I'm showing you or being exposed to. Let's go back to our letter X, our simple letter X, all blacks or all whites. Now, a computer already knows what an X is. If I show it an X, it knows it. But what if I showed it something that's similar to an X, but differs by a singular pixel? Now the computer has to say, well, is this really the same as an X? I know this slant up feature, that's what the computer knows, the feature, but I'm presenting it an image that's slightly different. So what am I going to do as a computer? I'm going to mathematically compare these arrays, and mathematically they differ by a single pixel, and mathematically they're 0.89% similar. So now the computer has to make a choice going through all the convolutional networks that we talked about, through hidden layers that I'm going to discuss with you, and determine, is this an X or is it an O or is it something else, before it spits out the output. The last thing before we get off of this sort of abstract computer science talk, before we look at actual real examples of computer vision and where we are in surgery, is the hidden layers, because people talk about this a lot and it's very confusing. What is a hidden layer? Hidden layer is actually the most intelligent part of a computer, where to me it seems as though it is thinking like we think. And hidden layers is like this. If I were to ask everyone here on the Zoom call, what is the color of the sky? And I give you options, A, B, C, D. You may at one point say, you know what, I live in a place where it's always a gray sky, so I'm thinking about gray, and I circle in gray. That's my answer. But then I rethink it and I say, you know what, that's actually because of the clouds. So I guess the sky when there's no clouds is blue, and then blue is my final answer. So all these changes that you think about before you submit your final answer is just like what a hidden layer is. That's what a hidden layer is. It's answers we never knew, that the computer thought about, may have changed their mind, and then ended up with a final answer. And so the idea here is that, again, we're talking about image classifiers. They don't really know every single thing out there. They only know what we taught them. And if I show it an X or an image that's slightly like an X, I need it to tell me that's an X that I'm looking at. If I show it an eye, I need to know that that's an eye. And if I show it the pancreas, I need it to tell me this is the pancreas. But a computer only knows what it knows. And if we only taught it a liver and a pancreas and a gallbladder, and I show it the colon, it doesn't know that. So it says, I don't know, it's a liver. I've never seen that before. It doesn't know. It just is an image classifier. If the image is not in the database, it will just come up with something that's irrational. And we can talk about errors, and later we will. But let's now go to reality, and where we figured out digital surgery in the realm of medicine, and then move into specifically surgery, okay? Pathology. We can now use a computer to identify visually a cancer cell from a non-cancer cell. One of the greatest papers to come out in the last 5 years is dermatologist level classification of skin cancer by deep neural networks. We now know those are convolutional neural networks, just using the exact same algorithm and idea that I already showed you, going round and round and round, right? And looking at features. And guess what? The computer is as good as a dermatologist at finding skin cancer. 4 years. This AI algorithm developed at MIT could detect a cancer in a woman's breast 4 years before a medical doctor did. If that doesn't shock you, I don't know what would. If you don't think AI is the future, you're lost. What about in endoscopy? I know a lot of the folks on here are GI experts. We use this in our endoscopy suite all the time, AI to detect polyps. Again, it's only detecting polyps. It doesn't know anything else. It doesn't know what a liver looks like. It only has been trained through training sets and thousands of examples to detect polyps and increase the ADR detection rates. What about actually surgery? What are the goals of computer vision? A huge part of digital surgery. What are those goals? Safety and identifying key structures, ureter, CBD, education, assistant, training surgeons, and ultimately better patient outcomes. And this is an important step towards truly computer-assisted surgery and taking robots from being master-slave systems that they are right now to more computer-assisted, giving the surgeon more information so that in the future we're operating based on information rather than just anatomic planes. Let's look at how we're applying a very sophisticated battery of technology, if you will, not just computers, but also other technology to visualize and help us in surgery. Here's an example where we have tattooed a colon lesion with ICG green, a biofluorescent dye, helping us to localize the tumor, which may not be evident with blue dyes, India ink, etc. This not only tells us where the tumor is and helps localize it, helps improve the vision, but also shows us, as we take the ileocolic pedicle here, where is the lymph node draining basin. So this has a future, and it's using a biologic or bio dye, biofluorescent dye, to enhance the target anatomy. Here's another great example. This is from neurosurgery. In neurosurgery, if you give somebody 5-aminolevulinic acid, actually given orally, if they have a glioma, an important kind of brain tumor, this tends to uptake in that glioma. They did a trial where they compared with and without 5' ALA, and what they found was this. If you use this dye to localize the tumor, your resection rates for a cure were higher, 65% versus 36%. Definitely statistically significant and a huge jump, actually. And more importantly, you had a higher disease-free survival, 41% versus 21%. So enhancing, in this case, fluorescent dyes, improves the outcome for the patient, right? All of this is for nothing if it doesn't improve clinical outcome. In my practice, we use lots of infrared markers, ICG. This is a transanal total mesorectal excision, and the Foley catheter, which is clear, has a lighted infrared stent in it. And here I'm doing the anterior dissection. Rectum is below. We're right in that plane between the prostate gland and the anterior rectal wall. The last thing we want to do is injure it. And you can see that is in the urethra and in the bladder. So it acts as a beacon, preventing injury to those key structures, like I showed you on the slide. We also can use ICG as well. What else can we do? Well, we can navigate the human body just like you navigate your car, okay? And how does this work on a human body? It's a little bit different and a little more complex, but it's the same idea. Think of a ceiling-mounted infrared detector as being analogous to a geocentric satellite. And there's two beams going to two things. One is the control piece that is in the surgeon's hand, and the other one is to a geofixed receiver that has to be stationary relative to at all times relative to the body. If that moves, then the orientation changes. And by the orientation, I mean for navigation on a human body during surgery to work, the real space, the actual patient anatomy, and the digital space can be a map like a MRI or CT scan. These Cartesian coordinates have to exactly match, or the whole thing is worthless. So a huge step is to get this accurate. How do we do this in the real world? In my operating room, we have our operating rooms are kind of sophisticated. They have intra-op CT scans right before surgery, the patient is scanned with these skin-fixed fiducials that we now generate a digital map that we can manipulate in 3 dimensions. And this allows us perspectives not otherwise afforded by actual surgery. Here, each of the fiducials is assigned a number arbitrarily, whatever we decide we want. Then we will now take a pointer and place it onto this skin fixed fiducial to teach the system where this is relative to the body so that we can navigate. And you can see the errors are just 3 millimeters, 1.7 millimeters. We like them to be under 1 millimeter, but the mean deviation is 2.3 millimeters. Pretty acceptable, actually, for what we need to do. Maybe not for neurosurgery, but for what we need to do. We now have the map. We've now able to navigate like you drive your car, the same thing. And we showed that this is possible. I'm going to skip through a lot. We don't have all day for all the pathways leading up to where we are. We're able to show that you can actually now do this in the world's first robotically. And this is first, before we do anything like that, we start in a dry lab here using just a model of someone's head or just a green model. And what you can appreciate is now that tip of the robotic scissor tip is being navigated. What I can do with that is not just see where I'm at the surface. I now understand and appreciate things in multiple dimensions from multiple angles, and I can direct my attention better. I can better understand, for example, where a tumor is. We did a lot of work doing this and finally figured out how to connect all the pieces and make this work for navigated cancer surgery of the rectum, both transanally and via standard robotic TME, low anterior resection for cancer. And this is actually a still frame showing that blue in the lower right. You see that blue pointer is where my scissor tip is during surgery, exactly in the correct plane of the mesorectal envelope above the endopelvic fascia. And this allows then, what are we talking about again? I'll say this again, is now the surgeon is able to operate not only with a 3D view of the anatomy, but now enhance the data set with digital information. Okay, just like how does a pilot fly? Or how does a pilot fly in the fog or the clouds? Then this whole visual thing, block it off. Block it off. You're not using that. You're flying by instruments, but really information. I know my altitude. I know my wing horizon. The same things apply. And this is the future of surgery. So I can take now I'm in a console, and robots are well suited for this sort of console type application, where now I have the optical data feed. I have an MRI image, and then I also have my navigated information to have more information in my hands, and I can enhance that with ICG. Let's look at an example. Here, before starting the case, this is ICG being given into the ureters. Now I have information about where my 2 important ureters are by ICG mode. Okay. Now I'm also going to put dye on the tumor itself. There you go. Now I know where the tumor is below the peritoneal reflection. I can still see it. Then I'm going to mobilize the, I do mobilization laparoscopically sometimes when it's a very low anastomosis. But the point is, we're able to see that ureter, sweep it away from the plane of dissection under the IMV, do the high ligation, do the splenic flexure mobilization, all that good stuff that we routinely do. And I know where my target that I don't want to injure is the ureter. I've done the high ligation, and there's my target left ureter. I can see it clear as day. And my colon is now mobilized, and I'm going to, at this point, dock the robot. Okay, so there's my 2 left and right ureter and the target anatomy. But I'm going to now further enhance the data set one more step using navigation. Now we've done all that stuff that I showed you, skin fixed fiducial, scan the patient, this time with an MRI, because we like the accuracy of that for pelvic dissections and rectal cancer. And now here I am. I'm navigating, and I'm visually identifying all these different aspects that are relevant for the dissection, the ureters, the tumor, navigated information to give me a complete full understanding of the case. I would just like to say that there was one case in this where we did a navigated total mesorectal excision that when I presented it to tumor board, because the margin was so close, they said, you're not going to be able to remove that with negative margins. Guess what? It was removed with negative margins thanks to navigation. So I will cut this short just because I know I'm probably running way over time, etc., and I don't want to, take too much time. But I also want to show you kind of work other people have done more on the order of using those convolutional neural networks that we spoke about earlier. Dan Hashimoto's group at Harvard looked at computer vision and surgery and really wanted to answer the question like why, how is this useful, etc. And they looked at, and rightly so, one of the most important kinds of operations that we do because it's very systematic, very controllable, and predictable, and that is the cholecystectomy. And they submitted thousands of these for analysis, image segmentation, etc. And they were able to break down the gallbladder anatomy into specific key safety zones or critical views of safety, as you already know, hepatocystic triangle, cystic plate, and the cystic artery and duct. And what they wanted to understand is where is the operation happening temporally? Like at what stage are we? If I were to show you an image, would the computer know what stage is this? And then spatially, in other words, what is the relationship of two instruments? And then the most difficult of these is conceptually, what is the surgeon thinking when they're performing a specific step? I'll just skip through some of this to say, really, if you look at the top two images, if training was a big impetus behind this, and what they wanted to show is, can AI be used to tell and direct a resident, for example, to know when their cutting instrument, in this case a hook cautery, is too low, and you see in the upper right, it's too low. You don't need to be there. You need to be higher up. Is this sort of educational guidance keeping surgery safe, what they felt was an important part. So they felt that that was a clinical need and will be a need in training and really in just surgeon safety. Let's also go back and remember that in those early 2000s, 2010 to 2012, when CNNs were developed, and people were using image, these image classifiers from the web, basically like Google Images and just like very rich image sources. That's what we want to create, especially for colorectal. And it's important in doing that we get videos, not just from one surgeon in one country, but all the world and all the countries. Why? Because this gives us an accurate representation of the diversity of surgeon styles and mixes of approaches, medial to lateral, lateral to medial, but also the diversity of patient population. That's very important that we don't have a specific type of population. Anyway, these are various different sorts of image databases that you can submit to. One thing that we want to understand is error. And error means, like I was showing you those examples, I gave you an image of a liver and you said it was a pancreas. That is not accurate. So how can we be accurate? In the world of AI, we talk about F1 scores, and this relates to precision and recall. And precision and recall, really, for all intents and purposes, are very similar to sensitivity and specificity in our world. And it can be defined mathematically as a harmonic mean as 2 over precision plus recall, with the inverse of that. But anyway, it's an error. What do we need to know about it? We're just surgeons here, okay? Is the F1 score. If it's very close to 1, that's great. That means this computer model is excellent. If it's very low, 0.2, 0.5, that's no good. And then that's not accurate enough to be usable. So this group of researchers looked at identifying different steps, and they looked at, identifying, for example, the IMA artery during LAR, and they found the F1 score is poor. Okay, but in other things it was good. For example, in Girota's fascia. So the model was good at identifying some key steps, but not all of them. Just to go quickly here, you see in the very top, those top two pictures, they show you an example where the computer, wow, it just perfectly nailed that vessel. It could tell you exactly where it was. That was the best performance, but my gosh, there was a lot of very weak performances where it just did not do very well, and thus had an overall low F1 score. Not a good model, not quite there yet. And there's different things, and basically a person goes and annotates every one of these, saying, hey, this is the plane of dissection right here. Can you learn that for me, please? See, this is the line we want you to understand. That's where we want to dissect. And the computer could get it, and then we give it the raw image, we annotate it, a human annotates it, and then it could recognize the dissection plane, but look at the F1 score, 0.05. So it could not do this very well. It did it once. We show you the example when it did it right, but most of the time it did not get it right. So the model needs more work. So we are in the stage still of model development. We don't have it right yet, but we'll get there. I'm going to end up the talk with a few other examples of what's happening currently now, like late 2024. This group looked at identifying different planes, and they used a model using CNNs and all the things that we learned about in first half of the lecture to identify the plane of dissection in real time doing a laparoscopic total mesorectal excision. And you can see that this is an adjunctive application. In other words, we're enhancing the data set. You can think of it that way. We don't just see the anatomy. We now have a computer also saying this is where you need to go. Okay. So this could potentially help, one, in training, but also in guidance in more complex cases. These are just some more examples. Again, this is happening in real time during real surgery, not I annotated images and all this other stuff that I was showing you where let's see what you can do in a video. This is in real time happening. Okay. So computers are now getting fast enough that we can train them to recognize tissue planes like this one to do a proper TME, and or it's a stepping stone perhaps to more complex identification of anatomy. Here's another one. In this training set, the neural network was taught to recognize the pelvic autonomic nerves, and you can see them here highlighted in a green color that allows the surgeon to know where those nerves are, which obviously we don't want to injure during a TME. So this is again happening in real time, happening so in a way that helps one see the relevant anatomy and preserve, do a nerve preserving TME. Here we're looking at the posterior dissection. Here's one more image just showing you the identification in real time of the pelvic nerve system along the posterior wall of the pelvis and sacrum. And here's just another example. And one more where you can see it just lit up after that rectum has been removed and you're looking down at the pelvis. A computer model is giving us this information. So computers need ample vision for this. And it's amazing that our computers, our desktop computers, the one you're on right now, is still growing exponentially. And we're not there yet, but it's estimated by what, 2060 or something like this, the average desktop computer will have the power of all mankind, all brains, at least if we continue on this exponential path of growth. You can see this is a few years behind. But there's a much more important and more fascinating than this, you guys, is the fact that we've completely gutted our computer architecture. These were called mainframes in the 1970s. All big companies, IBM and whatever, they had these big basements full of big, powerful computers that they used to do complex, problem solving. We don't have those anymore. The basements are empty. They're coffee shops. And they've been replaced with cloud computing. You and I, we're consumers, so we're familiar with the cloud. This is where we take our phone and we upload our pictures there and our emails in the cloud, and we totally understand the cloud. But what a lot of us didn't know is that the clouds for engineer are used for computing. They are doing the computation in the cloud. So they, for example, if they want a powerful computer, well, they can use 1, 2, 10, 1,000 computers to solve it all at once. They can just push a button and say, I want 1,000 computers to work on this right now. Just like that, it's done. The way that it's organized is brilliant and allows for this, processing that we don't have the time to get into. But the idea then is to have a cloud that maintains this information. How can we leverage AI and all this data? You know how many, there are several, I want to say 20 million minimally invasive operations done every year with tons of data. But how do we harness that data to make it useful? We have the data, we have those images like the Google images, but we don't know how to share them due to everyone working in silos and not having this connectivity. But the cloud can help with that. And the idea would be to have a cloud that connects everything. Let me give you examples. Let's say we have an array of robots, a surgical robot, a Da Vinci here, a Da Vinci there, or some other brand, doesn't have to be Da Vinci. In my R1 robot, let's say I taught it really, really well how to recognize the left ureter. And the R5 robot learned really, really well how to recognize the common bile duct. Well, guess what? Now R1 and R5 know the same information because all of that isn't stored in R1 or R5. It's stored up in the cloud. So this is leveraging the power of the cloud to share important information and have this collective surgical conscious. If you're not aware of quantum computing, you should be, because quantum computing is here to revolutionize the world of computing if it becomes more stable. Currently, if you haven't heard, Google's quantum computer solved a problem in 5 minutes that would have taken the fastest classical computer 10 septillion years. That's longer than we know than the Big Bang. Okay, so there is it's a whole nother world of computing. We're not there yet with stability, but it will be in the cloud. By the way, you can access quantum computers right now through your own laptop. So wow, that's a lot, right? Let's summarize with these ideas. Computer vision is one of the most important aspects of digital surgery and its application of AI, using those CNNs that we spent so much time trying to explain how they work. Robotic platforms, in my opinion, are very well suited for this multiplex, multi-information as a platform, because it allows you to work at a console, work like a pilot sees multiple forms of information and is able to interpret it only to enhance the understanding of critical anatomy. Real-time structure identification, as we saw in those last video clips, is very real. It's happening. This will be a part of surgery to have the enhanced information there at our fingertips. We're not there yet with the precision. And I showed you those models with the very poor F1 scores, right? The dismal F1 scores, 0.5 for identifying key planes of dissection. So our models aren't there. The clinical need, I think, is there, but our models aren't quite there yet. The future is promising, and it's hard for us to grasp or envision it. This is a photograph from 200 years ago. And it is the first photograph ever taken. I don't even know what it is. It's like blurry. What is it, a building? But that's not the point. The point is, could you think the person who took this photograph envisioned what we have today, 4K, 8K video transmission of the internet? We couldn't see the future then. And I think in surgery, we always have to, as we're pioneers too, we're pioneers and we're looking towards that future. Anyway, if you want to read more about AI, digital surgery, a lot of the things I spoke about are straight out of my computer vision chapter. I'll say nothing happens in a vacuum, and without my team around me, I'm basically nobody. So thank you very much for your time, and I'm happy to take any questions you have.
Thank you, Sam. That was a beautiful exposition, actually, and congratulations to all the work that you're doing. Phenomenal work. It's almost looks like something science fiction movies becoming true. Very true, actually. Surprisingly, actually, as clinicians, actually, at least in this part of the world, actually, we were not that very good in mathematics, so we chose biological science and we became clinicians. But you seem to be too good at mathematics too, actually. So for us, actually, we just use the applications of AI and see how it can be used in clinical system. And as you very rightly said, actually, I mean, we are also partly involved in this AI process. Actually, I always wished that I was at least 2 decades younger to going through this artificial intelligence or digital phase of surgery. But surprisingly, this new quantum chip of Google, the Willow, which showed that actually, even if you're alive for about 5 years from now, you'll be able to see whatever you want to see. So I mean, the way in which the technology is changing, actually, and the way in which the entire AI system is changing the world is phenomenal. Congratulations to you for being a pioneer in this field and taking this forward. And I'm sure it's going to immensely benefit the way we teach surgery, the way do surgery, and the way we prevent complications and the way we improve the outcomes of surgery. Thank you so much, Sam. There are some few questions here. Actually, Baiju, can I take some of the few questions that are raised here?
Good.
See, one of the questions raised is like you've shown beautiful videos live, you're doing the surgeries and you're superimposing images, you're getting into the planes. But the question Dr. Sanjay Sonar wants to know is how does one correct the change in the position? Because abdomen, neurosurgery, it's okay, we get all stable. I mean, it's a rock steady brain. But in abdomen, how is that you're able to maintain this position and take care of the elasticity of the organs and also the pneumoperitoneum that keeps changing during surgery?
That's a great question. And it's one of the reasons that navigation and abdominal surgery has never really worked. It doesn't work, but it does work in specific target organs as long as they're fixed. So yeah, you're right. The cranium very stable, spine also very stable. And then also the best accuracy is with bone, spine, joint, brain. No doubt about it. It is very challenging, but in specific aspects of fixed target organs, what is a fixed target organ in the abdomen? The pancreas. That doesn't move relative to the spine. What about the small bowel? Absolutely not. It's too mobile, so we cannot actually have that overlay of the maps working correctly. But the subperitoneal rectum is fixed and fixed enough to allow us to operate reasonably well. Are the accuracies 1 millimeter? No, I'll be honest. They're closer to 4 millimeters, but it's a step, and it is harder to do that. You're right. But yeah, operating in the abdominal cavity proper is more difficult. And this is why when we did the navigation, we mainly designed it to be with the transanal portion of TATME because we weren't in the abdominal cavity then, and we're dealing more with fixed targets, prostate, the rectum, etc.
Yes, Dr. Sanjay is in online. Dr. Sanjay, are you happy with the answer?
Oh, yes, very nicely answered. And the target organ, if it is not fixed, the parameters will keep on changing. The XYZ axis will keep on changing, and hence the localization may not be proper. Could we have annotations of live surgeries where the anatomical structures have been defined and then collate that data according to live surgeries which are occurring all around the world? I mean, the live surgeries, and we can annotate the data like you have shown that the neural network below the inferior mesenteric artery. can be localized. That way, if we can kind of enhance the accuracy of the data over a period of time, then maybe some years down the line, we can have better surgical prompts from the computer.
I totally agree. And I think that I think we hopefully eventually will. Yeah, I mean, your idea sort of is, let's take the live surgery, have it linked up to the cloud, have it interpreted in real time,
Right.
and annotate it in real time via the cloud, rather than some sort of in-house made AI system. And I think that, yeah, I think that is the direction and vision that we should be thinking about.
It's a very good this thing what Sam has told us. Actually, any general surgeon, GI surgeon who is practicing wants to get into this relatively fixed structures. I mean, like pelvic surgery, esophageal surgery, retroperitoneal surgery, and maybe to an extent urological surgery are the first ones to venture into this because they are relatively stable. Do you think agree with this, Sam?
I totally agree with it. Yeah, these are
Yeah.
fixed, especially retroperitoneal targets, like you said,
Yeah.
the entire urinary system, but especially kidney, ureters. Yeah, definitely.
And for GI surgeons, I think esophageal surgery is going to be a good thing to venture into.
It's very fixed. You're right.
Yeah, very fixed.
Yeah.
Yeah. Yes. Any other questions that we have? Baiju, you have anything from your side?
Yeah, actually, there are no much questions from the chat box. So, what will be the medico-legal consequences in the event of surgical complications in the era of AI?
What are the medical legal consequences? I think this has been a huge block to taking all of this rich data set and doing what was just suggested, having it up in the cloud and live interpretation, is that there's a medical legal block. But all these videos do not contain patient identifiers. And I don't know. Obviously, we're not just dealing with legislation in one country. We're dealing with something that's, affects the whole world, and all countries would have different policies. It's very difficult. It's a roadblock to our advancement.
Happy for every moment.
Yeah, very nice. This thing actually. See the way. I mean, the legal hassles actually. As we are talking about the legal hassles, actually, the legal experts from our side, they're also trying to incorporate AI into their practice. So I think we'll find a solution very soon. I think whatever legal issues we'll have. But AI is definitely going to play a big role. I mean, whether you like it or not, it's going to come into clinical practice. Actually, subconsciously, consciously, we're all involved. And whether you like it or not, you're going to get involved into the thing.
Yeah, for sure. I'm just looking at this one other question. Can image superimposition help during liver surgery and parenchymal transection? I think absolutely it can. And there is a lot of work on this from ERCAD in France, where they have shown successful models to help with liver parenchymal surgery. So yes.
Regulatory bodies actually see basically one thing we are very sure that you just cannot write an algorithm and start practicing. Like what we do in clinical surgery, each and every algorithm that is written has to go through FDA or the DCGA in India. Actually, it has to go through this and get validated and approved. Then only we can get into clinical practice.
Yeah, good point.
How does digital surgery impact the cost of healthcare, and is it accessible to patients in all economic brackets?
Well, digital surgery is not one entity. Digital surgery is an idea and approach to healthcare, and specifically in the operating room. And is it accessible to patients? I mean, the idea is that patients not even billed or whatever. This is part of the infrastructure of the operating room, the robot, and it should be definitely affordable to all patients. In other words, that they should not necessarily have to pay more for these sorts of things, or that would be the hope. I mean, ultimately, we do it so patients benefit. And our altruistic approach to patients, right, is always that, you know, we treat all patients the same. We don't care what is their economic bracket. Half the time we don't even know what it is here in the States anyway. So yeah, hopefully it is something that will be democratized, if you will, and available to all. But right now it's launching in pockets, meaning these ideas and this technology is not happening for everywhere. It's happening in specific centers and being explored. You know, we're exploring the benefit.
Goodbye.
Yeah, very right. Actually, for laparoscopic surgery to come into routine clinical practice, it almost took you about 3 decades. But the way in which IT is progressing, actually, I mean, I think it's going to take very less time before all this technology comes into accessible thing for everybody, actually. And I think it's going to get cheaper very fast as compared to laparoscopic or robotic surgery.
And also you can integrate images like laparoscopic ultrasound along with the AI and show the structures which are to be safeguarded, is it not?
And what has been the patient reception? I tell you that when we did this case that I described, for example, that the tumor board, everyone, you know, a whole group of surgeons said, there's no way you can remove that with negative margins. And when it was, and by the way, this lady has now been cured for 6 years, basically is cured. You think she's thankful? She's very thankful, but patients don't really understand or appreciate the technology. You know, that's a side of our practice that basically patients are naive to. They don't know what we're doing in the operating room. You know, they only have a rough idea. There's a tumor, we're taking it out. They don't really understand or appreciate the true value of these elements, but we do.
Any other questions, Baiju, from your side?
Nothing from here this
Yeah.
side. Can development of the last question you can take. Can development of dynamic annotation be answered to stereotactic annotation for mobile organs?
Wait, what?
Second last question.
Can dynamic annotation be answered to stereotactic annotation for mobile organs?
Let me see.
Too technical a term for.
Oh, can I
Dr.
develop?
Abhishek, can you explain? He is on the line. Abhishek, can you please explain your question?
Yes, like
Development of dynamic annotation be answered to
pre-op
what do you,
stereotactic mapping
yeah.
instead of something like dynamic annotation.
Yes, yes, this is actually yeah. Gotcha. All right. Yeah, I got you. Yeah, I think it is possible. It's not possible using stereotactic navigation the way I showed it, but there are other models that potentially can actually be able to track mobile organs. And this also is work that's being done at ERCAD in France with Jacques Marescot's group there. So I don't personally have experience with this, but this is a whole nother, you know, sphere of image guided surgery that is being explored for sure.
Thank you, sir.
Yeah.
There is another question. What are the limitations of current digital surgical technology and what are the developments on the horizon to address these challenges?
Yeah, there's so many challenges. I don't know about limitations. I feel like the sky is the limit with digital surgery, but also we're using this term kind of loosely, right? I think what's closest on the horizon is to be able to operate with an enhanced data set. This is very analogous to if you know, just like we use this also in other aspects. For example, you take a car from today's time, a 2025 model, 2024 car. pretty much all of them come standard with there's an object in your blind spot, the mirror has a flashing light on it. Is this correct? Like, versus 15 years ago, that didn't exist, or however many years ago. So these become things that enhance our understanding while driving a car. This is the closest reality that we're going to see in the operating room in the next 5 years or so, is this constant enhancement of the visual data set. That's what I think is real and approachable. What I don't think is near or within the next 5 years is true automation of a robot. Does a robot go in and operate for you? We're not quite there yet. There are models that actually do this in a dry lab or in a cadaveric model setting, but we're not ready for that in humans right now. So the enhancement of the visual field using various computer interfaces and ways to enhance the data set are realistic.
Dr. Sanjay has got another question. Dr. Sanjay, can you open and ask the question directly?
Yeah, Dr. Sam, can we put some markers on the organ like liver at 3 points and then make the computer aware that these are the areas where the liver is, or this is how it has been retracted, or on the colon?
Yes, you can. Well, the liver is more realistic. So that's what they do, is they sort of make a mini model in ERCAD of the liver. So they put those points, like you said, on the liver. And now anywhere I remove the liver, the model moves too.
True.
It understands where everything is because of those fixed points. But the colon is it's too pliable. It's not like an object that you can just move around so smoothly. So I don't know of any work being done with small bowel or colon like that. But liver, yes, they have been able to show that if a liver moves, that the computer model can keep track of where it now is.
Right. It is like RFID. So you can tag that organ, and that organ gets picked up by the computer.
Yeah, you can tag the organ. I mean, usable ideas, speaking of tag the organ, is what we want is safety awareness. Like if a plane is flying too low to the ground, it warns you that you're too low. We want the same thing in computers to help guide surgeons, for example, in understanding that potentially that's where the ureter is, or be careful, you're very close to the ureter. You know, those sorts of things could potentially improve safety and then thus outcomes.
Thank you so much. You have been very helpful.
Thank you.
And all the best in the research.
And then Abjit has one comment. Do you envision humans becoming digital slaves? We kind of already are digital slaves. But do we, I don't know. I think the future is, I mean, this is actually not a silly question. Who knows what the future holds? I think robotics is poised to grow dramatically, and AI is already taking leaps and bounds every year. I mean, just think 2 years ago, we didn't have ChatGPT, and now every single college student is using ChatGPT for everything, to help them study, to help them write essays, to help them everything. So yeah, I think there's a huge, we're on the precipice of big changes in AI, digital surgery, and everything else that can benefit.
Absolutely. Yeah, we are living, actually, our generation has seen both ends. Open surgery, to laparoscopic surgery, robotic surgery, digital surgery, everything. Our generation has seen.
Yeah, we're lucky to be living at this time. We're to see so much evolution. A lot of us can remember back before there even was an internet. So it definitely is something. It's a time to be alive, a time to be contributing, a time to feel good about the future and get excited about it, especially for all the young people on the webinar. That's what you should be very thankful that you're living in this amazing boom time, of great growth. And it's an opportunity for young people, and especially in surgery, to get involved and to be a part of that huge change that is going to happen, period.
So thank you so much, Dr. Sam ATALLAH, for accepting our invitation to present this wonderful work.
Thank you so much.
And I request Dr. G.V.RAO to wind up, say a few words. Dr. G.V.RAO. Dr. G.V.RAO. You are muted.
Yeah, thank you once again, Baiju, for that unwavering academic activities that you have been doing for the last so many decades. Thank you again for getting so many experts across the globe onto this platform to share their views, so that a lot of people who don't access to these international experts have seen what's happening across the globe. Thank you for all the participants who have participated in this. Thank you, Sam, for the beautiful work that you're doing, and I hope you come up with more innovative things in future which can really change the outcomes of surgery. And we're looking forward for more such interactive sessions for Baiju's platform, which are going to be of immense benefit to not only to training the surgeons who are practicing, but also to youngsters who are getting into practice. But one thing for sure that I think all the youngsters, you have to be in pace with, or you have to know some amount of artificial intelligence to practice. Otherwise, you'll be a no voice in future. I think you have to be in pace with what is happening, whether you like it or not. They'll get into the clinical practice, and I think we have to be in to compete with our peers across the place. I think we have to know something about artificial intelligence. Thank you once again, Baiju, for the excellent session we've had.
Thank you, Professor G.V.RAO. Thank you, Dr. Sam ATALLAH. Thank you, Dr. Abhishek, for introducing the speaker and moderator. And thank you all the participants across the globe who have joined for this wonderful webinar. We will meet next time. Thank you all. We are signing off.
Thank you.